Today I'm going to present my research topic, modeling and analysis of metal additive manufacturing process using FEM approach. So I'll start this presentation with an introduction of metal additive manufacturing process along with its certain aspects. After that, I will be discussing about a short literature review based on that I have found my study. After that, I will be discussing about my framed objective one by one, and after that, the conclusion of the study. So I'll start with the presentation now. First of all, what is additive manufacturing and its classification? According to ASTM F2792, additive manufacturing is defined as a process of joining material to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing process. However, according to ISO ASTM 52900, additive manufacturing processes are basically categorized in 7 types. That is material extrusion, material jetting, wet polymerization, binder jetting, powder bed fusion processes, directed energy deposition processes, and sheet lamination process. Among all these 7 types, powder bed fusion processes and directed energy deposition processes usually utilize metal feedstock. So here, right side, we can see that a further classification of DEDAM process based on its feedstock. The left side, we have feedstock in the form of wire, and then the right side, we have feedstock in the form of blown powder. In wire type of DEDAM process, we have wire and arc additive manufacturing process, which utilizes low cost arc welding type machines, which certainly qualifies it as a low cost alternative to powder bed fusion processes. In this slide, we can see that different constituent elements basically form a metal AM setup. Here we can see that the 3 main constituents are heat source, motion system, and feedstock supply. These 3 constituents basically controlled by a CNC controller. After that, in metal additive manufacturing process, basically heat source comprises of high energy beams and electric arc power. In high energy beams, we have laser and electron beams, and in electric arc power, we have different type of arc welding processes. After that, to interpolate the heat source, we should need a motion system. The motion system is basically utilized by using industrial robots and CNC machine, and at some instances, the combination of these two can be used. After that, for feedstock supply, we have dedicated machines in which metal feedstock has been supplied in the form of powder and wire. In powder, there are 2 types of material supply. The first one is powder bed, and the second one is blown powder. So here we can see that in the left side, this process is basically powder bed fusion process, in which we can see that a small gear type structure is being deposited. However, in the right side, we can see that on the upside, we have this blown powder technology, in which you can see that the powder is being blown concentrically to the laser power source, and this cylinder type structure is being formed. However, in this lower diagram, we can see that we are using a metal inert gas based welding machine for the fabrication of this component utilizing a industrial robot. This slide basically is showing some process attributes and some other attributes related to WAAM and PBF process. It is very important to compare these 2 processes, WAAM and PBF, on the basis of certain factors, in which we can see that on the basis of geometric complexity and surface finish, powder bed fusion processes are far advantageous than wire and arc additive manufacturing processes, because it can be used for the production of very high complex components, as well as it yields a better surface finish when it is compared to wire and arc additive manufacturing process. However, the power source which is the prime constituent of any metal additive manufacturing process, is a standard arc welding process compared to a very high cost laser with optical system in PVF process. Apart from that, process efficiency is greater than 80% as it is found in any arc welding process. However, in powder bed fusion process, because of a lot of irradiations from the laser beam, the process efficiency lies between 20% to 40%. After that, deposition in wire and arc additive manufacturing process, deposition is as high as 2 kg per hour, whereas in powder bed fusion process, it is 10 gram per hour. In this slide, we can see that this is a schematic representation of wire and arc additive manufacturing in the form of industrial robot and in the form of CNC. In this figure, an industrial robot is used for the deposition of this component, in which this welding torch is being coupled in the end effector of this industrial robot. However, in this CNC machine, the welding torch is coupled at the tool holder joint. Now it is important to understand why we need 3D printing process to print. To answer this question, we have to refer this component given in this figure. This component is basically CFM LEAP jet engine 3D printed fuel nozzle. And initially, when 3D printing process or metal additive manufacturing process was not invented, it is fabricated with the help of different conventional and unconventional manufacturing process. So with the help of those processes, first 20 different small parts were manufactured, and after the complete manufacturing, it is assembled to form this complete shape. After that, it can be sent for the application. However, after the invent of 3D printing process, this whole component can be fabricated in one go. So based on that, its fuel efficiency has been increased by 15%. Due to less wear and tear, its service life is increased by 5 folds, and due to topologically optimized design, its weight is reduced by 25%. So that is how we can conclude that the 3D printing process for this type of component is very far suitable when it is compared to any conventional or any other type of manufacturing process. Now, we must know that if we want to produce any component, is it possible to manufacture with the help of any metal additive manufacturing process, or for that matter, with the help of any additive manufacturing process? So we must refer this video in which we can see that a cylindrical type of structure is being formed. And we can see that a continuous heat accumulation is being formed, and this heat accumulation is producing this dramatic rise and fall of temperature during the deposition in the component. However, this dramatic rise of temperature causing severe consequences. The consequences is in the form of residual stress and distortion produced in the component. Because of the residual stress produced in the component, we can see that the component got delaminated from the substrate before it goes to the application. And because of that, this part qualifies as a failed product and it cannot be further utilized. So we must understand that whether our component could be possible to be printed with 3D printing process or metal additive manufacturing process or not. So for that, it is important to first analyze that will it be possible to print our component with the 3D printing process or not. For that, first we have to understand the thermal cycles, and based on that thermal cycle, we have to predict the residual stress produced in the component. So it can be done in two ways. The first one is numerical modeling technique, and the second one is hit and trial experimentation. And we can see about these two types of approaches in the next slides. But before that, we must understand what is the need of numerical modeling approaches. So in any type of additive manufacturing process which utilizes metal feedstock, there are seven different types of defects shown in this slide has been occurred. We can expect any kind of these defects like porosity, deformation, surface finish, poor surface finish, or maybe crack, oxidation, delamination, and residual stress. And as we can see that residual stress are mostly found in all the type of these different type of alloy systems with more than 50% occurrence percentage. So it is important to model residual stress before we should print the component, and after that we can obtain that it is going to be failed. As we have discussed that during the deposition process and after the deposition process, a component produced through the WAAM process may experience different type of defects like porosity and other defects. And residual stress are the important defect which further causes different type of defects like distortion in the component, like delamination in the component, low fatigue life, and high stress corrosion cracking, and like that. To deal with this situation, we have two approaches: hit and trial experimentation and numerical modeling approaches. In hit and trial experimentation, we have to perform experiments, and after that we have to do some empirical formulation, and after that we can be able to find the desired values of process parameter which can be able to control these defects. However, in numerical modeling approaches, only we have to do numerical modeling with the help of some dedicated computers and other gadgets, and after that we will be able to find different process parameter which is responsible for sound production of additive manufacturing component. So it is less cost consuming compared to hit and trial experimentation. Then we must just understand what is the residual stress. According to Zhu and Lu, a stress state which exists in the bulk of material without the application of any external load or other sources of stress such as thermal gradient is called a residual or internal state. It means that when the component has been processed completely and it can be sent for application, at that point of time, if there is any stress trapped inside the material, those stress are called as residual stress. Well, while the application, those stresses can be harmful to reduce the surface life of the component. Therefore, it is important to predict the amount of residual stress and means to reduce it before the component can be sent for any application. In wire and arc additive manufacturing process, this slide showing the mechanism of the formation of residual stress in the component. And we can see that in this video, molten pool is being formed during the deposition process as the this welding torch is advancing. And at one instance, behind this molten pool, the solidified layer is being formed because the heat source passes the specific point. So in this figure, we can see that this schematic is showing the formation of different isothermal contours in which this small red color ellipse is basically the molten pool. However, these bigger ellipses are showing different isothermal contours with different temperature values. As this deposition direction, as you can see the deposition direction, it means that this molten pool keeps on moving in this direction, and behind it the materials get solidified as soon as this point is passed at certain location. So it is showing that in front of this molten pool, the compressive state of stress is forming in here at this location. However, at the back of this molten pool, as the materials is getting solidified, tensile stresses are formed. Because of that, first compressive stress are being formed, and then it is converted into compressive yield stress. After the weld torch has been removed, it starts reducing and at certain point of time it changing its state from compressive to tensile, and it reaches to point D. After that it reaches to point E, and this yellow bar is showing the amount of residual stress which remains inside the component once it reaches to room temperature condition. Based on this understanding, I have found a bunch of important keywords which is responsible to find relevant gaps, and based on that, I have proposed a few objectives related to modeling and experimental analysis of additive manufacturing process. So the objective of this study is to first develop an FE-based thermomechanical model which is able to predict the transient temperature and residual stress distribution in the deposited component. After that, it's real-life experimental validation, and after that, an investigation of different process parameters with the help of developed model. So I have basically a complete methodology given in this slide. So the objective of this study is to investigate the temperature history and residual stress in the component produced through the wire and arc additive manufacturing process. So we have two approaches. The first approach is finite element analysis, and the second approach is experimentation. However, experimentation here is necessary to validate the finite element analysis as well. So based on the FE-based thermomechanical modeling, first I have performed the thermal modeling, and after that I've performed the structural modeling while utilizing the predicted temperature, time temperature history from thermal model as an input to structural model. After that, after solving the structural model, I have got the residual stress profile. Similarly, from the experimentation, I have measured the temperature profile during the deposition process and the residual stress values after the deposition process, and I have compared these two values, and after a satisfactory comparison, this model has been further utilized for parametric investigation. So this slide is basically showing the modeling procedure. The first three points are like a standard input to any finite element engineering problem solving procedure. So geometry modeling, material modeling, and mesh sensitivity study. After that, point 4 to 7 are very specific to these type of modeling, because this modeling is basically a model of moving heat source. So process parameter selection is based on some pilot experimentation, then element activation and deactivation algorithm, and thermal and mechanical boundary conditions, and moving heat source modeling. So these specific points are discussed in the further slides one by one. So this model is basically thermomechanical model. So two different type of physical phenomena is happening simultaneously, such as thermal as well as mechanical. So in any FEM software, we must couple them to capture capture accurate transient temperature profile as well as residual stress distribution. In FEM software, we have two different type of couplings. So we have this thermal model and structural model, and then we have an interaction zone. The first type of coupling is fully coupled, in which for every time step, the thermal and structural model are solved simultaneously. After that, it goes into second step and further steps. However, in the second form, sequentially coupled model, the thermal model are solved, complete thermal model are solved at the first instance, and after that, extracting the time temperature history from this thermal model, which is being fed into structural model. And after inputting this temperature history in the structural model, we can now solve the structural model to predict the residual stress value. After that, material model. Material model is basically an important input to thermomechanical model, because this type of processes basically involves interaction of temperature from room temperature to very high value of around 3000 degrees Celsius or even more. So it is important to give a temperature dependent different material properties as an input to this type of models. So now for thermal model, we should need density, thermal conductivity, and specific heat. In these three different diagrams, it is given, the values are given. Apart from that, for mechanical model, we should need Young's modulus, coefficient of thermal expansion, yield strength, and tangent modulus. So for my experimentation, actually, I have utilized IS 2062 mild steel, which is equivalent to ASTM A36 mild steel, and ER70 S6 big wire. So this table is representing this elemental composition. As a second input, element activation and deactivation algorithms are an important one. As I have utilized Ansys APDL software, this element activation and deactivation algorithm is called as element birth and death approach in that software. So this slide is basically showing that approach. So here in actual practice, actually, what we did in welding or in wire and arc additive manufacturing process, as the torch moving over the substrate, it continuously depositing the malted material, which are further formed into solidified layer, and it keeps on depositing to form the final component. However, in FEM practices, it is not possible to add elements with respect to time in any particular solver. So for that, what we have to do, we have to completely model, geometrically model all the elements representing the deposition zone at the beginning of the modeling. However, during the before the beginning of the solving procedure, we should deactivate those elements representing the deposition zone by issuing ekill command. After that, in the second picture, we can see that as the heat source approaches at the first instant of this hashed section of this element, as it is going to be deposited with respect to time, dedicated time, these set of elements are activated using ELIve command, and after activating those elements, the heat source are being deposited. This process basically continues until the complete layer deposition is formed, and again it keeps on repeating in cycle until the deposition of complete component is being completed. So this is basically element birth and death approach. However, thermal modeling and mechanical modeling utilizes different type of element birth and death approach separately. The third important input in this thermomechanical modeling processes are moving heat source analysis. This type of analysis is basically an analysis of moving heat source. A continuous heat source is moving to deposit the layer, and we have to capture the amount of heat being produced by this arc welding process and delivered it into substrate or into the feedstock. So based on an extensive literature review, I have found that Goldak double-sided heat source model is the best suited for the modeling of arc welding process as the moving heat source model. In this figure, we can see that a substrate is shown on which in the red color we can see that this is a double ellipsoidal shape molten pool. This red color zone is basically representing the double ellipsoidal molten pool. This area is basically representing the frontal part of the double ellipsoidal. However, this area is representing the rear part of the double ellipsoidal. Based on the variation of heat input, as we can see with the help of this skewed normal distribution, we have different percentage of heat input in the frontal ellipsoidal, as well as we have different amount of heat input in the rear ellipsoidal. So for that, we have two different type of equation, which is representing the front heat input and the rear heat input. Only the difference here is we have to compute these value AF, B, C, and AR, B, C. These are basically the Goldak double ellipsoidal heat source parameters, which can be calculated with the help of pilot experimentation of a single bead. We will cover the calculation procedure of these parameters in the further slides. So this slide is basically showing a complete flow chart of thermal model and mechanical model. So in here, we have to do some material modeling and geometric modeling and other type of in pre-processing procedure. As a part of element activation and deactivation algorithm, we have to deactivate all the layer which is associating the deposition zone. After that, thermal boundary condition. Now we have to apply some do loop for the selection of layer. For the first, we have to choose first layer, then second layer, then third layer. So we have to apply a do loop for that. And for element activation also, as I have described it in the previous slide, we have to use a do loop for the selection of appropriate set of element which is being activated during a particular instance of time. So based on these standard inputs in the code-based model, we can be able to perform the thermal modeling. As the thermal model finishes for our dedicated geometry, we will be able to extract time temperature history from that. Time temperature history extracted from thermal model can be inputted into this mechanical model, and a similar set of procedure, a little different from thermal model, is also applicable for this. And after solving, the mechanical model will be able to find the predicted residual stress value at different locations. So to run the model and to check the values of transient temperature and residual stress, I have basically developed a case study. So in this case study, actually I have deposited 8 different layers in zigzag deposition formation, and we have a substrate. The dimension of substrate is 200 by 100 into 8 mm. However, the length of deposition is 110 mm. So for the deposition of this component, I have basically proposed 2 case study. The first case study is a layer-wise reduced heat input strategy, and the second case is layer-wise constant heat input strategy. So after solving the thermal model, this slide is basically showing the contour animation of thermal model, in which we can see that a layer are being deposited with interlayer idle time, interlayer cooling time. During the layer deposition, as we can see, the temperature is reaching around 2800 degrees Celsius. And in this complete process, during the deposition of individual layers, the maximum temperature is ranging between 2500 degrees Celsius to 3000 degrees Celsius. Further, in this slide is basically showing a contour animation for residual stress value in x direction, so that sigma x. So during the deposition, as we can see that the value of sigma is going around more than 1000 megapascal. However, due to heat treatment effect, during the cooling stage, the values are reducing and reaches between 500 to 800 megapascal. So after the development of model and prediction of various responses from it, we are intended to do some experiments for the experimental validation. For the experimental validation, I have basically developed this CNC welding torch interpolator for the deposition of straight thin-walled deposited component. And for that, I have actually utilized this EWM Phonics GMAW MIG welding machine with the pure argon gas cylinder. And I have utilized this stepper motor and Arduino control board for the control of torch in XYZ direction. So this is the close-up view of this deposition zone, in which a substrate plate is clamped at 4 different locations, and the torch is about to deposit the component. Apart from this, I have utilized K-type thermocouple, which is located at different locations, which I will discuss in further slide. So this slide is basically representing, as I was discussing about moving heat source parameter, Goldec double ellipsoidal moving heat source parameters. So this slide is basically showing a procedure. So first I have deposited a bead on plate component. After that, sectioning it through wire EDM machine, and after polishing and etching of the component, I have recorded different parameters. So this A value is basically half width, R value is the reinforcement height, and C value is the depth of penetration, and AF and AR values are the ripple mark, frontal and rear ripple mark, which is basically an important input to the Goldtech double ellipsoidal heat source parameters. And after that, for the measurement of temperature, transient temperature distribution, I have actually utilized NI data acquisition system, in which a dedicated card is used for the recording of temperature along with these three different key-type thermocouples. And for the recording of temperature into a computer, I have used MATLAB software. After that, for the recording of residual stress at various locations, I have utilized this portable X-ray diffraction system. So according to the plan given in case 1 and case 2, I have recorded residual stress value along line AB and MN. So this is a long scale deposition specimen, and this is a short scale deposition specimen. However, the location of point A1 to A4, B1 to B4, and point 1 to 5 here are different, and the residual stress values are measured on those points only. So this video is basically showing the deposition of my specimen for experimental validation. This slide is showing the deposited component. The first two deposited components are representing those two case studies which I have discussed in previous slide for the model validation. And this component is for mesh sensitivity study. And these four components are related to parametric variation study along with those samples as well. These samples are representing long scale deposition, and these samples are representing 4 different case studies of small scale deposition. So once we have predicted our predicted temperature value from the model and measured temperature value from the experiment, I intended to compare it at 3 different points, TC1, TC2, TC3, on which thermocouples were fixed. So in these figures, this figure is representing TC1, TC2, and TC3, and the continuous blue line are representing the values predicted from the model, and this star is representing the values measured from the experimentation. We can see a complete similarity between the trend of variation between these two types of results in all those locations. However, there are some differences of magnitude which does not exceeds 10% between it. After that, this slide is basically showing the comparison of residual stress in X direction along the line AB. So blue line again is representing the values predicted from the model. As apart from that, these red dots are representing the value measured from the experimental sample and XRD machine at different pointed A1 to A4 and B1 to B4. Again, there is a complete similarity between trend of variation. However, at these 2 points, there are a slight variation of magnitude. As we have validated the developed thermomechanical model with the help of experimental value, now based on that, I have proposed a case study to investigate the effect of various parameters like heat input and travel speed on residual stress based on these different 4 cases. The case 1 basically describes a single layer wise heat input system, whereas case 2 and case 3 basically describes variable layer wise heat input system in the form of 2-tier heat input system for case 2, 3-tier heat input system for case 3, and 4-tier heat input system for case 4. So for that, a little modification related to a do loop for the choice of different cases has been done in our developed code, and it was then further executed for different cases. As we want case 1 to be executed, a parameter named LWHY was specified according to value 1, 2, or 3 for which is representing case 1, case 2, case 3, and case 4. Once we have predicted different temperature and residual stress value, it is further compared with the experimental value. After the comparison, comparing temperature, these three different plots are showing TC1, TC2, and TC3. And after comparing temperature at these locations, I have found that the maximum error in temperature prediction is 10.97%. However, the minimum value is 0.4132% during the layer-wise deposition. Now, based on the proposed methodology, I have to first ensure that there is sufficient metallurgical bonding are there or not. So for that, I have extracted a maximum peak temperature associated to different layers for all the cases as shown in this figure. This is for case 1, 2, 3, and 4. So case 1 is basically a single heat input strategy. So we'll discuss it later. Apart from that, case 2, case 3, and case 4 are variable heat input system. So in here we can see that this red dot line is basically showing 1450 degrees Celsius temperature, which is the melting point of the feedstock I have used. So after the deposition, during the deposition of first layer, as we can see that the temperature is going way beyond 2500 degrees Celsius in all the cases, as the heat input for the first layer in all the cases are same. However, during the second layer deposition, the temperature of first layer, which is being represented by blue line, is exceeding that 1450 degrees Celsius value, which is the melting point of the feedstock. It means that during the second layer deposition, the melting of first layer is also occurring due to the heat addition of second layer. It means that since the first layer is also melting during the deposition of second layer, it means that it is creating a good metallurgical bonding between second and first layer, and this process keeps on repeating because the heat accumulates during the deposition process, and this causes a good metallurgical bonding between every individual layers. After that, as I have proposed different layer-wise heat input strategy. So in case 1, as I've used constant heat input, so the temperature profile is almost constant. This green line is basically showing the maximum peak temperature, which is ranging between 2500 degrees Celsius to 2800 degrees Celsius for case 1. And for case 2, as the heat input are lower, then higher, lower, then higher, like that. So temperature again representing a little variation of temperature, higher, lower, like that. However, the same type of variation are more visible in case 3 and case 4, as the value of heat input are varying more compared to case 2. So here in bottom of this graph, a green line is basically representing the minimum temperature achieved before the deposition of every layer. So in the case we can see in all the cases, the value of minimum temperature are increasing as the layer keeps on depositing. However, maximum temperature are being constant in case 1, and little variation in case 2, as considerable variation in case 3 and case 4. Apart from that, minimum temperature keeps on increasing. The value of minimum temperature increase is in the case 2, which is 198 degrees Celsius. However, this is the maximum of 220 degrees Celsius in the case of 4-tier system, which is case 4. After comparing the thermal fields, in this slide, a comparison of longitudinal stress values according to line AB is shown. So the trend of variation is similar among all the 4 cases, as well as the experimentally measured results are again showing the same trend of variation, but which is basically validating the predicted results from the model. Now we can see here the indigo line is basically showing the state of stress in case 4, which is the least among all the proposed case study. So by adopting a 4-tier heat system compared to a single-tier heat system, we can reduce the maximum value of residual stress in X direction in the case 4. After that, this slide is showing the transverse state of stress. Here again, we are observing the least amount of stress in case 4. And this slide is basically showing the value of equivalent stress, that is von Mises stress, and for different layers. Initially, the value of equivalent stress starts increasing up to the 3rd layer, and after the 3rd layer, because of the heat treatment effect, it keeps on decreasing, and it finally settled at some certain value. In case 1, we can see that the value is around 406 megapascal. However, in case 4, it is around 333 megapascal. By considering case 1 value as a reference, we can observe that there is a slight increase of equivalent stress by 1.02% in case 2. However, there is a significant decrease of 6.41% and 17.94% in the equivalent stress has been observed in case 3 and case 4. Respectively. As the stress I was discussing is on the substrate, this slide basically showing the stress comparison of stress in the deposited component. During the first layer deposition, after the first layer deposition, the value of sigma x, the x direction stress observed in the component is around between 200 to 250 megapascal. However, it keeps on decreasing due to heat treatment effect as the second or onwards layers are being deposited. At the final layer deposition, after it reaches to room temperature condition, the upper surface of the top layer is experiencing the compressive state of stress, which values is ranging between 0 to minus 50 megapascal. These are the conclusion of the study. As I have proposed 4 different type of cases, like single tier heat input, 2 tier heat input, 3 tier heat input, and 4 tier heat input system. So in 3 and 4 tier heat input system, it has been observed that there is a maximum variation of temperature by 8.62% and 13.6%. However, these values are 5.35 and 5.21% for case 1 and case 2 respectively. So if we have to consider the dimensional accuracy of the component, like the layer width and height, so that we can observe or we can deposit previously decided layer height and width. So we have to go with the case 2 such that 2-tier heat input system strategy. However, if we have to care for residual stress, since we are giving the lowest amount of heat in case 4, because of that, case 4, the component produced through case 4 is observing a reduction of 13.07% and 25.83% of longitudinal and transverse stress in the component when it is compared to case 1. So case 4 is recommended where lowest residual stress values are desirable. So these are the research deliverable. So based on the research and findings, I have published 2 review articles in 2 different journals, which is covering all the state of art literature survey related to metal additive manufacturing process in the form of wire and arc additive manufacturing process and powder bed fusion process. After that, this study basically gives an experimental validated transient thermomechanical model for additively manufactured component. Based on utilizing that thermomechanical model, we can predict temperature profile and residual stress in the component of any length, any width, any height. On the basis of mesh sensitivity, a computationally efficient model, transient thermomechanical model, has been developed. And apart from that, a CNC gantry setup for the fabrication of straight wall builds through the WAAM process. These are some future scopes related to this work. As I have not modeled the microstructure and phase transformation effect in this model can be further utilized to model microstructure and phase transformation effect for the modeling of residual stress in the component. And this model can be further enhanced to develop and deposit complex geometry component. So these are the references. Thank you. If you have any questions.